Data science frequently hits a wall when predicting binary outcomes: pass or fail, survive or die, true or false. These results exist in only two states, with nothing in between. Applying ordinary least squares linear regression to this data is a mathematical violation. OLS is designed for continuous variables, expecting a relationship that moves across an unbroken spectrum. This scatterplot shows why the straight line of OLS fails. The observations are locked at 0 and 1, but the regression line extends infinitely in both directions. This geometry creates nonsensical results, like predicted probabilities that fall below 0 or exceed 100. A probability of -12% represents a structural collapse of the model. This is an engine failure, proving the linear approach is incompatible with binary data boundaries. Modeling these outcomes requires a different geometry, one that bends the linear output and binds it within a strict 0 to 1 range. The solution begins with the Bernoulli distribution. This is the parametric framework specifically designed for data consisting of absolute ones and zeros. In this framework, the model target changes. We no longer estimate a raw value, but isolate mu, the exact probability an outcome equals 1. While OLS equates the linear predictor with the fitted value, logistic regression treats them as separate. The linear predictor, xb, and the fitted probability, mu, occupy distinct mathematical states. This split screen contrasts the standard OLS equation with a logistic model output from the R console. Understanding the pipeline between these two views is the key to converting abstract linear predictors into real-world probabilities. Navigating these mathematical states allows a single model to provide both relative risk assessments and absolute predictions. The mathematical bridge of the model is the Logistic function. The right side is the standard linear predictor. It is the sum of the model's coefficients and variables. The left side is the log odds, also referred to as the logit. This function maps the linear predictor onto an S-curve. It forces the output to stay within the 0 to 1 range, regardless of how high or low the input variables go. While the link function solves the geometric problem, its raw output, log odds, is unintuitive for stakeholders. Interpreting the model requires converting these values into a readable format. This three-tier view maps theory to practice. We have a single predictor model in the R console, underlying math, and the raw binary dataset. Looking at predictor x, the coefficient value is -1.504. The literal interpretation of this coefficient is that as variable x moves from 0 to 1, the log odds of y changes by exactly -1.504. A change in log odds is mathematically precise, but it is an impractical way to communicate risk to a medical provider or a business client. Analysts apply a specific sequence of calculations to this coefficient to extract a more actionable metric of relative risk. The first transformation involves exponentiating the coefficient. By taking the constant e to the power of -1.504, we calculate an odds ratio of 0.222. The odds ratio represents the ratio of the odds of success when variable x is present versus when it is absent. In this model, the odds of an event occurring given x equals 1 is precisely 0.222 times the odds when x equals 0. Expressed inversely, the odds of the event happening when x is 0 are approximately 4.5 times greater than when x is 1. The odds ratio is highly effective for showing relative risk, but it does not provide the absolute probability needed for final predictions. The final step derives the exact probability, mu, using the inverse logit function. We take a calculated linear predictor value, in this case, -0.4055, and plug it directly into the formula. This abstract negative number resolves into a bounded probability of exactly 40%. This result maps directly back to the raw observations, providing a clear statistical expectation for real-world events. This sequence transforms an abstract regression slope into a concrete percentage, finally making the model output directly actionable for decision-makers. These calculations are only useful if the underlying model parameters are statistically valid. Analysts must evaluate the uncertainty. We focus on the standard error and the z-statistic. The standard error measures the accuracy of the estimate, while the z-statistic dictates whether the predictor contributes to the model in a meaningful way. For odds ratios, the threshold for significance is exactly 1.0. This forest plot shows several confidence intervals relative to that baseline. If a confidence interval crosses 1.0, the analyst fails to reject the null hypothesis. The predictor is not statistically significant. Rigorous evaluation ensures that analysts do not mistake noisy data for genuine predictive insights. There is a common misconception about what a confidence interval represents. It is not a 95% guarantee for a single range. Under frequentist logic, a 95% confidence interval means that in repeated sampling, the true parameter will fall within the calculated range 95 times out of 100. The entire logic of the model follows a specific path. We start with the linear predictor to find the log odds. We exponentiate to find the odds ratio. Finally, we apply the inverse logic to find the probability. Logistic regression is most effective when the analyst can map the logit link to the specific requirements of the problem, extracting categorizations, risk ratios, or absolute probabilities as needed.